Can you imagine a world drenched in steam, potentially hosting life far beyond our own planet? Researchers are uncovering remarkable evidence that suggests there are water-rich celestial bodies out there, specifically sub-Neptunes, that may hold vital clues in the quest for extraterrestrial life. For scientists dedicated to the study of astrobiology, the hunt for life beyond our home planet often begins with one fundamental question, akin to asking in a parched desert, where can we find water? Among the myriad of exoplanets discovered thus far, a prevalent category has emerged, characterized by their interiors brimming with water. These relatively smaller yet intriguing worlds are referred to as sub-Neptunes, as they possess size and mass measurements that fall between those of Earth and Neptune. Interestingly, most sub-Neptunes orbit their stars at distances significantly closer than Earth's path around the Sun. This proximity results in surface conditions that are typically too scorching to sustain liquid water, or, consequently, any form of life as we know it. Instead, these planets are likely enveloped by thick atmospheres filled with steam, hovering above layers of an exotic water state that cannot be categorized strictly as a solid or liquid. The concept of these intriguing steam worlds was first posited 2 decades ago, sparking increased interest in their intricate compositions and evolutionary processes ever since. In an exciting development, a collaborative team of astrobiologists and astronomers hailing from the University of California, Santa Cruz has crafted a more sophisticated model to study these steam-dominated worlds. This innovative framework is aimed at uncovering more about their elemental makeup and how they came into being. Understanding the formation mechanisms of the most commonly identified planets in the cosmos allows us to pivot our focus towards examining the less common exoplanets that might actually support life, articulated Artem Agishin, a postdoctoral researcher at UC Santa Cruz and the lead architect of the new modeling approach. Their comprehensive findings were detailed in a study published on July 24th in the Astrophysical Journal, featuring contributions from Professor Natalie Batalla, who leads UC Santa Cruz's astrobiology initiatives, as well as Professor Jonathan Fortney, the chair of the university's Department of Astronomy and Astrophysics. For the first time in the history of space exploration, the James Webb Space Telescope, JWST, has verified the existence of steam on several sub-Neptune planets. Astronomers are optimistic that JWST will uncover dozens more examples, underscoring the necessity of these advanced models to correlate observations made from the exoplanet surfaces with their internal characteristics. Previously, the models used to analyze sub-Neptunes were predominantly adapted from studies of the icy moons within our own solar system, such as Europa and Enceladus, which orbit Jupiter and Saturn, respectively. Agishin remarks that sophisticated modeling can provide invaluable insights into what discoveries telescopes like JWST unveil about sub-Neptunes. Unlike the smaller icy moons, which are basically compact bodies with layered structures, consisting of icy outer shells over liquid water oceans, sub-Neptunes are markedly different. They boast much greater masses, ranging from 10 to 100 times that of Earth, and they orbit significantly closer to their stars. This means that, in contrast to the icy crusts and liquid surfaces found on moons like Europa and Enceladus, sub-Neptunes evolve thick atmospheres composed of steam and layers of something known as supercritical water. Supercritical water is an unusual phase formed under specific temperature and pressure conditions, presenting complex behaviors that differ greatly from standard liquids or ice. Some scientific models suggest that within the extreme pressures and temperatures found in sub-Neptunes, water could morph into an even more fascinating substance known as superionic ice. In this intriguing phase, hydrogen ions can flow freely within an oxygen lattice, facilitating unique chemical reactions. To accurately model sub-Neptunes, researchers must comprehend how water behaves in various forms, as pure steam, as a supercritical fluid, and under severe conditions such as those found in superionic ice states. The team's modeling incorporates experimental data about water's properties under these intense conditions, and enhances the foundational, theoretical modeling necessary for further study. Battaglia emphasizes the significance of these planetary interiors, describing them as natural laboratories for examining environments that are difficult to replicate within a terrestrial setting. The implications of what we may learn about water worlds could lead to unexpected applications that we have yet to imagine. As we progress, we might discover that a specific subset of these water worlds serves as new habitats for potential life in the galaxy, she noted. By meticulously modeling how water is distributed among these prevalent exoplanets, scientists can trace its movements throughout the formation of planetary systems, enriching our understanding of one of the universe's most prevalent molecules. Agishin highlights some of the fascinating attributes of water that support life's complexity. Water functions as both a chemical acid and a base, thus participating in essential chemical reactions. It possesses the unique capability to dissolve salts, sugars, and amino acids. Through the formation of hydrogen bonds, water boasts heightened viscosity, a raised boiling point, and an enhanced capacity for heat retention. Life can be defined as complexity, Agishin stated succinctly, and water's diverse properties enable this very complexity. Looking ahead, Agishin reinforces that their modeling doesn't merely present static images of sub-Neptunes. Rather, it emphasizes their evolutionary trajectory over millions and even billions of years. Given the fact that planetary characteristics undergo significant changes over time, understanding this evolution becomes indispensable for making accurate predictions. The models they've created are poised for real-world tests through ongoing observations with the JWST, as well as through forthcoming missions, like the European Space Agency's Planetary Transit and Oscillation Plato satellite. Designed to hunt for Earth-like planets within their host stars' habitable zones, Plato will provide a valuable opportunity to assess the integrity of these models and refine them based on observational data. Plato will enable us to validate the accuracy of our models, while also pointing us toward further areas for refinement, Aguichin explained. In essence, our models are actively predicting outcomes for upcoming telescopic explorations and shaping the future discourse around life beyond Earth. Reference: Evolution of Steam Worlds, Energetic Aspects, by Archim Aguichin, Natalie Battaglia, Jonathan J. Fortney, Nadine Nettleman, James E. Owen, and Eliza M. R. Kempton. Published on July 24, 2025, in the Astrophysical Journal. DOI 10.3847-538-4357, add 935. Stay updated with the latest discoveries. Sign up for the SciTech Daily Newsletter.